So Professor Yan is going to give us a talk about his flexible funded project around monitoring of CO2 flow. So please go ahead, Professor Yan.
Okay, thank you, Dr. Brown, for introducing me. My topic is about measurement of CO2 or monitoring of CO2. Topics very different from the previous one, or different from perhaps any other topics in the UKCCSRC series. Okay, moment. Yeah, and I'd like to just summarize why do we need to do this measurement. If you look at the CCS stages here, from capture plant to transportation to final storage site, you have several key stages. In each stage, we need to measure captured CO2 for the good reasons. We need accurate accounting of what's happening in the CCS system for emissions trading or for optimized CCS system control. So that's all required basic data from measurement. Okay, not only for trading or accounting, also we need to monitor any leakage from a CCS system. Not only say short term, we talk about in a few years, even decades. For example, if any leakage from a storage site. To give you an example here, how important CO2 measurement. Imagine you have a large power plant which emits 20 million tons CO2 per year. If there is a 1% uncertainty in CO2 metering, that could end up 8 million euros financial exposure. Okay, so this is based on 40 euros per ton CO2 in February 2021. Now, CO2 flow is a quite difficult flow medium. It depends on pressure or temperature, and the CO2 could be in a gas form, could be liquid, could be a two-phase, I mean gas-liquid two-phase mixture, could be supercritical on the top right corner. Okay, for transportation purposes, for efficiency, normally we prefer dense phase. Okay, that's all people talk about in the CCS industry. But all this changing phase of CO2 makes measurement very difficult. Okay, so why is it difficult? What we want to do is we want to know mass flow rate or total mass of a process. Okay, simply because of the rapidly changed phase in CO2. So mass gives us more accurate accounting. So unfortunately, on the current flow metering techniques, they can measure volumetric flow rate, not mass. Okay, there are good proven flow meters such as radiological systems or NMR, nuclear magnetic resonance instrument. They work okay. However, they are very expensive. We talk about £500,000 in that price range each. So they are not widely accessible, especially for CO2 emitters. Okay, so a lot of people working in this try to use a conventional volumetric flow meter such as orifice place, the Venturi tube, a turbine. All this really the results so far are not really satisfactory. I know some companies, some unit groups, they're developing ultrasonic meters to monitor CO2 flow. So I think that's perhaps useful, should I say. But more successfully, as my team has worked on in the past few years, Coriolis mass flow meter is a very good option. Okay, so you will soon later on. But this technology good for diameters less than 150 millimeter. For anything larger than that, we have to have different technology. Okay, not only for flow metering, also leakage detection. There's potential leakages from pipes, capture facilities, storage site. We can monitor flow, temperature, pressure, and use chip sensor. But how do we do that? How effective that is? You will see later. We made a good program, but a lot is still to be done. And when we do the CO2 flow research, we need the facilities. Okay, but there are very few, like we call that calibration facilities designed for CO2 flow. That's really difficult across the globe. Okay, relatively easy to do simulation, I have to say. So that's that. I want to stress that any CO2 data will help to inform the legislators, regulators who make decisions Okay, so otherwise the legislations may not be really realistic. Okay, so for example, the accuracy of CO2 flow, total mass, and so on. Okay, so that is why we are conducting research with the support of UKCCSRC. My team has received funding from UKCCSRC 3 project, not only most recent flexible funding awarded last year, we have received 2 previous ones, as you can see here. So my results include the recent one, also the previous one, because they are interrelated. And as I said earlier, we need a test facility to do our research. Okay, otherwise you can't. This is experimental. It's applied research. This is a simplified CO2 flow test rig. You can see here is a 25 millimeter bore. Okay, so 1 inch internal diameter. And we have all the regular equipment, such as weighing systems to provide absolute reference. We have various pumps, separators, compressors, and so on. We have a gas phase, liquid phase, and 2-phase, simply because by changing temperature, pressure, you easily get a 2-phase CO2. So we have horizontal tax section, vertical tax sections. Okay, so this is a simplified schematic drawing. You can see the some complexity of the system. Here's the system. You can see the actual arrangement. Okay, this looks quite a complex machine. Actually, this is a CO2 test platform. For this system, we can achieve a very good reference, say 0.6% for liquid by pure weighing method. Okay, it's kind of like absolute reference. Also, if we use a master flow meter to calibrate, we can achieve 0.16 or 0.3% for liquid and gas CO2 respectively. And for this rig, we can achieve single phase CO2, pure liquid, or pure gas, or mixtures. We can also add impurities into the system, just to recreate likely what would happen in real capture plant. There are impurities. Okay, so that's where we are. And I'd like to show you some video clip can say what is CO2 flow, is proper CO2 flow under CCS conditions. So this is a highly stratified flow, and you can see low flow rate at 40% gas volume fraction. You can see in the flow is highly stratified, liquid at both lower level is horizontal flow. And this one, we double the flow rate, you can see the CO2 bubbles within liquid CO2 on the lower level pipe. And also, you can see the gas phase on the top. Now, if you move to, we double flow rate further, so nearly 2,000, 2 tons per hour. So you can see it's well developed. We call it fully turbulent, fully developed flow. Okay, now what we're trying to do is to measure the flow rate accurately, regardless liquid, gas, mixtures, or stratified. So this actual setup, so we can see in the part of the test platform. Also the Coriolis flow meter, which we worked with our industrial partners. So such meters is widely used in a range of industries, but we are assessing the suitability of such meter in CO2 flow under CCS conditions. And more importantly, we try to develop such technology for CCS. So what you see here, this is a Coriolis flow meter. You can see 2-phase flow going into the flow meter, in and out. You can see in the vibrating tubes. So this tells you roughly how flow meter, such flow meter works. You can get this Q dot. This is a pure mass flow rate, non-volumetric pure mass flow rate, kilogram per hour per second. And for mass flow rate, you can achieve plus minus 0.1% of pure liquid. Okay. In addition to that, we can get density of the fluid in the mixture. However, this is works very good for pure single phase. Now, if you have a 2-phase, such as CO2 mixture, liquid and gas, then very large errors will be there. So you can imagine, because the bubbles create a lot of trouble for the meter. Okay, then we try to develop a method to improve accuracy of Coriolis flow meters for CO2 2-phase flow. And the idea is very simple. We have data-driven models that's based on a neural network, a supported vector machine, or deep learning models or combination of any of them. We take input, output from chloride flow media, such as the apparent incorrect flow rate, the apparent incorrect density under two-phase conditions, of course, fluid temperature, difference of pressure. That goes through the SIS. We can do laboratory training offline. We can do on-site training. We can produce accurate CO2 flow and total mass, plus all the information we need, such as gas volume fraction or density impurities. So that's the strategy we have adopted. And you can see we are not changing anything hardware. So the system is very cost effective. Now, a typical results here, and I don't have time to go through detail, but I summarize. On the vertical text section, so CO2 flow moving upwards, two-phase. Okay, you see gas volume fraction here. You add a little bit, add more. So mass flow rate, it has a very large area. It can go minus 12%, plus few percent. It's go all over the place. So you can imagine if you use such a mid-term CO2 two-phase, it creates a lot of trouble for accounting purposes. And with our data-driven modeling approach, we can reduce that area to plus minus 1.5%. Okay, so this is really encouraging. Okay, no cost, very little cost implications here, just software work. Okay, so that's that. For gas volume fraction, you talk about plus minus 10%. It's slightly large areas, but fortunately, from users' perspective, they want accurate liquid mass flow rate. So move on to horizontal setting, very similar situation here. So again, we apply our data-driven approach. We can reduce areas such you can see mostly plus minus 1.5%. Okay, on the extreme low flow rate, you got fairly large areas. So we are still working on this in order to reduce errors under very low flow rate conditions. Okay, so this is really demonstration of results. Now, next issue is CO2 flow in CCS systems not always steady. Depends how you operate your plant. If you operate your CCS plant in a flexible way, okay, it's so-called smart plant. The CO2 flow comes in and out. Okay, if the plant is off, on, it's a rapid cycling, or reduce the load. So CO2 flow become big, large. So there will be a lot of transient conditions. So you have how do you measure flow rate accurately under dynamic flow conditions? That is actual difficulties. Okay, so unfortunately we don't know very much about transient CO2, particularly under two-phase conditions. So this is our setup. Okay, on the test rig. In addition to our chloride flow meter, we obviously look at the pressure, look at the temperature. Also, we apply even camera high-speed imaging system, look at how the CO2 flows under dynamic flow conditions. So imagine a startup. We start a plant. So what happens to CO2 flow in the system? So initially it's gas phase. Then you can the liquid come in from left. The push over, you can say. So we are trying to measure the flow rate of such flow under transient conditions. And we want to know what really happened in the CCS system under flexible operating conditions. So we can look at what happened to the flow rate during the startup process, flow rate. Also density, what's happening there. Okay, so there's a lot of data like this will help us to understand the whole dynamic process. So again, we can try imitate shutdown process. You stop and pump. Okay, you open the release valve. You can see the mass flow rate coming down like this. What happens to density? Why is like this? Similarly, you can see sometimes very complex. Of course, you can look at the pressure drop, the temperature drop. So such data will help us really understand, interpret transient systems if you're trying to have a flexible operation of a CCS plant. In addition to the chloride flow meters and the pressure, temperature transducers, even high-speed imaging, we also apply the capacitance method. You can multiple electrode, similar to tomography, okay, the similar system. And we can also observe what happened inside the pipe. On the right, you can see this, this is actual capacitance sensor itself on the rig. You can see here. It's quite a big metal block, okay, and this is really heavy duty, you can see. because of the pressure involved. Okay. Now, recently we conducted some leakage detection. Okay, again under CCS conditions, we modify the rig such that we can let CO2 to go into atmosphere. But again, we apply cost-effective sensors in the acoustic emission. Okay, we effectively use sensors to listen to the process, how CO2 leak from a facility. In addition to temperature sensors, of course, pressure as well. So actually, this is the setup. It's in the column, have the source CO2. This is the sensor arrangement. You can see the AE sensor. They commonly available, widely used. We use this for many different projects. So once you have AE sensor, it's acoustic emission. You have a so-called sensor signals. We do a range of processing. Here's an example, which give a power spectrum, okay, of that signal. So this spectrum contains information about what's going on in the pipe, what kind of CO2 is a liquid, any impurities, okay, and leak rate, and so on. So again, we use the same approach. So we develop data-driven models. We analyze acoustic emission signal characteristics. We plus traditional temperature output, and we can work out leak rate. So how many kilogram per second CO2 is being leaked. Also, we can see if any impurity. If we use nitrogen as an example, we add to CO2, see what happens. Surprisingly, the results are pretty good. Okay, so the top one is leak rate. Okay, CO2 from that rig is you can errors mostly within plus minus 2%. For a measured volume fraction of nitrogen, the impurity again is very good. I have to say this is really impressive. Okay, we're not doing any detailed chemical analysis here. It's just AE, okay, acoustic emission signal analysis, plus some models. Okay, so that's that. So pretty good. Summarize what I have presented. Okay, Coriolis mass flow meters with data-driven models, provided you train them properly, you can produce fairly accurate mass flow of CO2 under two phase. Okay, I mean gas liquid mixtures. So that's that. Now, if it's pure liquid, you talk about you can achieve 0.15%. If it's gas CO2, you talk about plus minus 0.25%. Okay, so pure CO2 flow, gas or liquid, much more accurate. Okay, that's will help enhance the CCS applications. And data-driven modeling is really good. Okay, in this occasion, you talk about you make a system, CO2 flow metering, cost roughly 10K. Okay, it's much more affordable and realistic. So for leakage detection, also very encouraging. Similar technology, cheap sensors, data-driven models, we worked very well. I must say we made good progress, but also significant further work is required. Finally, I would like to acknowledge UKCCSRC. Without their funding, my team can't do research as such. Okay, that's really good. I'd also like to thank North China Electric Power University, also Tianjin University, both provided very valuable support in making this applied research possible. Okay. Last but not least, my industrial partners in the UK, and they provide really invaluable support. Finally, my contact details if you wish to contact me. So I stopped there, Dr. Brown. I spoke less than 20 minutes.
Yeah, no, you did very well to time there. Thank you. Thank you for the really interesting talk. So we've got one question from Johnson in the chat. I wondered whether I could take Chair's prerogative and jump in ahead of him and ask whether you had looked at the when you considered impurities, have you looked at the distribution of composition in the liquid and vapor phases when you have that kind of stratified flow, or do you have the capability of doing that?
We haven't gone that far yet. As you can see from my slides, we are at the moment we are adding nitrogen gas to CO2. We can monitor the volume fraction. So under leakage conditions, we over the next few months we're trying to measure flow rate of CO2 with impurities. Aim is to produce the estimate what impurities in the system, what's in the fraction. Okay, So you talk about distribution, we haven't gone that far. Maybe we can try our capacitance method, high-speed imaging, but I guess it's not straightforward because it's such a small quantity. It could be anywhere in the system.
Yeah, I'm sure colleagues at UCL will be able to comment. But I remember some years ago that the distribution of things like hydrogen, nitrogen in a gas phase were of a particular concern to pipeline operators. So if you created such a stratified flow, would you get pockets of essentially non-condensable gases coming out and staying in places that you didn't want it? So I think there's a real practical driver for that kind of information, for kind of compositional behavior between phases in two-phase flow.
Good. This comment there is very good for us to consider what happened next. It's good to know there's such a requirement. Our focus, you can see, is to measure flow rate detection, regardless chemical ingredients. Now it looks like we're adding nitrogen gas in the system, we can detect. We may be able to do something similar, but the distribution, I guess, is challenging. But we will have to consider something we could do in future.
I said some years ago, we published a paper when I was at UCL looking at the impact that impurities have on outflow rates from releases, and it might be worth. I'll send it over. It might be worth you looking at.
Oh, be good. Thank you, Solomon. Yes.
Just onto Johnson's question, then, how much does the flow profile of CO2 affect the accuracy of the measurements?
Well, regarding this particular approach, say Coriolis flow meters with the data-driven modeling, we have studied the impact of different flow profiles on accuracy. I can't say no, but there's minimum impact. Okay, so as you can see, this is quite common for all two-phase, three-phase mixtures. Flow profile always there, but I have to say for this technology, I think we are fortunate. The flow profile have very limited impact. Okay, the data presented here, the horizontal, vertical, the accuracy plus or minus 1.5%. They have a lot of different profiles already, highly stratified, fully developed, all the funny stuff. We are included. We see all that. Okay, so again, this is the beauty of, should I say, machine learning method. You could train the system with all possible flow regimes. So all the cases are considered. So that's that.
Thank you. Great. Are there any other questions from the floor? Feel free to just unmute and then ask. While we wait for someone else to jump in, I wondered. So with the acoustic emission measurements you had there, do you have some kind of secondary mass flow measurement just to double check? I remember being involved in some experiments where an operator were looking at venting operations, and we had considerable issues in having an accurate measurement of the flow rates during that kind of regime. So I just wondered whether you kind of had a double check of the data you gotten from those.
Yeah, and the data are presented from leakage detection there. We have this weighing scale as absolute reference. So since we weigh the whole thing, regardless the phase, whether gas or liquid or mixed, it doesn't matter. So that is pretty good. If we could in future try to apply flow meter as well, the Coriolis flow meter, again, that give us more like in another kind of reference later. So I think the data pretty reliable, yeah, in terms of reference.
And did you have any information about where the CO2 will flash when it comes out? I wondered whether you had any kind of visual information about where that flashing propagated.
Good question, Solomon. Can I just ask my team? Some of my team are here today. I haven't observed myself in that. Is Saudin here? Can you answer that question from Dr. Brown? Sorry, probably he's not here. Yeah, we haven't. Personally, I haven't noticed this. Yeah.
Okay. Yeah. Again, it was a.
So
from previous experiments, it was you got the flashing propagating back into the release pipe.
Yeah, we have, my team had a lot of experience in collaboration with the Transient team to design rig working safely. You know, you top of the rig, you top 72 bar pressure up to, so safety is paramount. So
yeah, I mean, it's again,
we try to minimize anything like the, flashing back energy, because otherwise we have trouble. So so we have external safety people come to inspect the whole thing periodically. So therefore, I haven't heard anything like this. But anyway, I think something you have to bear in mind. So if we see this in future.
I think if you did the practical issue was that if you got two-phase flow propagating back into your vent, then you would get the temperature drop, and then you had to worry about freezing.
So yes, indeed.
Yeah.
On this case, in the column, you got the liquid or gas mixture. By the time come to the leakage section, it's already gas phase.
Okay. So
that's where we are. But as you say, maybe we can feature create more challenging, the two-phase or something more, you say sudden leakage from a liquid tank. See what happens. Again, that's part of the difficulties my team facing, because you want to do something, okay, but under laboratory condition, you can only do so much.
Mm.
We have trouble like this for impurities. Sometimes impurities is okay, sometimes you can't do it because of risk.
Yeah, no, I remember such problems. I think maybe again colleagues at UCL might want to take you up on some experimental data. I think so. We've reached 3 o'clock. So I think if there are any questions, then I would encourage people to take them directly to Professor Yan or to Professor Tang. Thank you very much for attending. They were both really interesting talks, and I look forward to seeing everyone again. So thank you again, guys.
Thank you. Cheers. Bye-bye.
Thanks, everyone.
Thank you very much.
Thank you, Carrie.
Thank you very much, and thank you, Solomon, for chairing as well. Thank you.
Thank you, colleagues.
Yeah, thank you.
Yes.
Yeah, thank you, everyone.